خب بسم الله الرحمن الرحیم. امروز روز دوشنبه هست 16 خرداد ماه 1401. جلسه 16 هم هست، هم 16 خرداد هم جلسه 16 accidentally رو هم افتاده. Today we would like to wrap up estimation with variable mean. As you remember, we tried to decompose the original random function into a deterministic component, trend or drift, and a stochastic component. When it comes to deterministic component, we argue that we could borrow basis function from polynomial or trigonometric function or hyperbolic function or Fourier function or for that matter orthogonal function, eigenfunctions. But like finite element method, it's quite traditional to implement polynomial in various software. X of S could be considered as a n-degree polynomial in 1, 2, 3, 4, 5, 6 d dimension. And this can be written as k from 1 up to t sub n d, which is basically we denoted by t. A sub k, f sub k, s. As you can notice, you have to be quite clear on various aspects of this representation. First of all, it's spatial coordinate. Your spatial coordinate could be 1D, x, 2D, x and y, 3D, x, y, z, or in d dimension. The index of summation could go from 1 to p, where p is the number of terms corresponding to n-degree polynomial. These a sub k are considered to be undetermined coefficient. These f sub ks are monomials of a given n-degree polynomial. Monomials of a given n-degree polynomial. It might be interesting for you to try orthogonal eigenfunction representing your monomials of a given n-degree polynomial, and then compare and contrast your estimation process with that of traditional polynomial in 1D or 2D or 3D, and see if you are going to get any enhancement in your cross-validation statistics. When it comes to variable mean, we have scenario number 5, where your mean is variable and given and your variance is constant. When it happened that your mean is variable, then your current random function is no longer stationary. Your current random function is not stationary. Which means when it comes to y, covariance of y is not available. We try to derive the Kriging system in terms of covariance of W, because W is stationary, by the way, and you know why. It has three properties required for stationarity. Expected value of W should be independent of spatial location, which is the case. Expected value of W is 0. Variance of W is constant. Variance of W is the same as variance of Y. And then the covariance of W will be a function of atom separation vector, which is required for stationarity. Therefore, in this case, we manage to derive the Kriging system in terms of covariance of W, J from 1 to n, lambda J, which is the function of S0, and this has to be multiplied by covariance of W, Si, Sj, and this has to be put equal to R sub W, S0, Sj, Si. J is defined internally. You have to define I externally. You have n equation with n. Because we are given m, it really doesn't matter whether it is constant or variable. When we say we are given m, that means we are given this coefficient. Because we have already access to monomials of a given n-degree polynomial. That means if you know m, you can switch from y to w, and then you can easily delineate covariance of w. Because you do know a single partial realization for W. Therefore, it is okay to use this equation. There is no further argument on how to use this equation. You do have access to covariance of a stochastic component because you do have a single partial realization of W. When it comes to scenario number 6, you still have variable mean, but your mean is not given. And of course, your variance is constant. Again, if you ask me to comment on the nature of parent random function as well as the stochastic component, I would say your parent random function is not stationary. Why? Because m is variable, but your stochastic component is stationary. Because m for w is independent of spatial location, variance of w is constant, and then the covariance of w would be considered to be at most a function of separation vector. However, there is a minor, fragile difference between scenario 5 and scenario 6. In scenario 5, you manage to delineate covariance of W. But in scenario 6, you do not have access to a single partial realization of W because you do not have any M. These coefficients are not given to you. In this case, you will run into a paradoxical problem, an egg and chicken problem. And if you remember, I tried to get away from this paradoxical problem by saying you have to delineate a trend-free direction in your original parent random function y, and then use that direction to delineate variogram of y, and you then pretend that this variogram is variogram of stochastic component. And of course, this is part of your responsibility to have a glance at the number of textbook written on geostatistics, trying to compare and contrast this scenario with this scenario as far as this paradoxical problem of having access to covariance function of W is concerned. Therefore, here we could easily derive the Kriging system in terms of covariance of W or variogram of W. If you want to write it in terms of covariance of W, it's going to be summation j from 1 to n, lambda j, which is the function of S0, and R sub W plus k from 1 to p mu sub k times f sub k computed at S0 R sub W as a function of S0 SR. J is defined internally, K is defined internally, therefore you have to define I externally. Your anti-essence condition or universality condition is going to be I from 1 to n, lambda I, which is the function of S0, You have to multiply this by f sub k, si, and then put this equal to f sub k and s0. Again, if you look at this relationship, I is defined internally, therefore you have to define k externally. Altogether, you have n plus p equations with n plus p unknowns. And your unknowns are vector lambda, vector mu. You can express your Kriging system in terms of variogram as well. Why? Because R sub W, Si, Sj plus gamma sub W, Si, Sj is equal to sigma to the power of 2. This sigma to the power of 2 is constant variance. If you replace this R with sigma 2 minus gamma, you can easily write down the Kriging system in terms of variogram of W very easily. It's going to be minus j from 1 to n gamma W times lambda lambda j, which is the function of S0, times gamma W Si, Sj, plus k from 1 to p, mu sub k, f sub k at S0. This has to be equal to minus gamma W S0 Si. Once again, you have to define I externally. I should go from 1 to n. And your unbiased condition would not change. Lambda I f sub k Si, this has to be equal to f sub k at S0. Question. If you are told that your mean function is a first degree polynomial in 2D, if you are told that your mean function is a first degree polynomial in 2D, which means that this k should go from 1 to 3. And a sub k times f sub k, and this s has to be replaced with x and y. A1 plus A2 times x plus A3 times y. That's going to be a 1 degree polynomial in 2D. You are told that your deterministic component is going to be a first degree polynomial in 2D, and then you are asked to expand this summation here. How you are going to proceed to expand that summation out there. In a sense, you are asked to compute vector lambda and vector mu. How you are going to treat this problem. If I want to expand this relationship, it should be, for that case, I have to put k from 1 to 3, and then I have to put mu k times f sub k, and then x0, y0. X0, Y0 is the point under consideration where you want to have an estimation. You have to multiply mu sub k, mu1, by f1, which is 1, plus mu2 times x f2. F2 is basically x0. Plus this is how to expand this relationship if you are told that your deterministic component is a 1 degree polynomial in 2D. If you look at our lecture notes on last Monday, it seems that we left step 10. In step 10, we have to do additional computation if required. Do additional computation if required. And in geostatistics, step 10 concerns with computation of various variances. Variance of true value, variance of estimated value, and variance of residual. By the way, I remember I denoted the first scenario 5 by simple universal Kriging or universal simple Kriging. And we denoted scenario 6 by universal ordinary Kriging. When it comes to step 10, which is computational variance, you have three sort of variance. Variance of y at a point which is not sampled. As I said, and I would like to repeat that again, variance of y at S0 is the same as variance of W at S0, and they are constant according to scenario 6. Therefore, that's going to be sigma to the power of 2. Global variance, that's constant variance out there. And then when it comes to variance of estimated value, we denoted this variance by sigma, and then we put universal ordinary decreasing and then raise this to the power of 2. This is variance of estimated value. How could it be possible to compute variance of estimated value? Any comment? Any feedback? Could it be possible to compute variance of estimated value, assuming that the variance of parent random function is constant? If you are given this question as a comprehensive exam question, and you are asked to see if you can compute variance of estimated value, how you are going to proceed to compute variance of estimated value? Up to now, we covered this for 5 scenarios, 4 constant scenario and 1 simple universal decreasing. At first, you have to ask yourself, what is this? Y hat. Y hat at the generic point S0 can be written as I from 1 to n lambda I, which is the function of S0, and this has to be multiplied by y at S. If you want to answer this question, you have to ask yourself whether this linear combination is an admissible linear combination. Under what condition you will consider this to be admissible? This linear combination is admissible if the summation of coefficient is this coefficient here. If this summation is 0, then you can go ahead and compute variance of this linear combination. If this is not equal to 0, this summation of lambda I, then you can't continue computing variance of estimated value. Here, this summation of lambda I from 1 to n is not equal to 0. It's equal to 1. Why? Because if you put k equal to 1 here, f sub 1 is 1, regardless of the argument. Therefore, summation of lambda I is equal to 1. It's not equal to 0. Therefore, this linear combination is not admissible. It's not possible to compute variance of this linear combination. Not possible. And even you might raise another question when you are here. If you are asked to compute variance of this linear combination, one possible way is to say, okay, I can write this as lambda I lambda j covariance of SI Why did we not pursue this route? Variance of y cannot be written as a double summation lambda I lambda j r sub SI right? This is because y is not stationary. If y is not stationary, then you do not have access to covariance of y. Therefore, you cannot write this as double summation lambda I lambda j r sub y is by SJ. Variance of residual. By the way, if you are in scenario 5, Mr. Ahmadi, if you are in scenario 5, simple universal Kriging or universal simple Kriging, variance of true value is going to be this because variance is constant. How about variance of y hat? Could it be possible to compute variance of y hat? Let me write it here because I have some more comment to make when it comes to scenario 6. When it comes to scenario 5, variance of true value at the point which is not sampled can be written as sigma 2, this constant value. Now, when it comes to variance of true value, estimated value at a point which is not sampled, either scenario 5 or scenario 6, you can write this variance as variance of the stochastic component. Because variance of y is the same as variance of w, regardless of the argument. Therefore, variance of y hat is the same as variance of w hat. This deterministic component has nothing to do with variance. And then, if you look at your lecture note, you will notice that here we manage to compute variance of estimated value. How? Because we could write this as variance of I from 1 to n, lambda I WSI. Here, we are not going to ask ourselves whether this linear combination is admissible or not. Why? We are not going to ask ourselves because W here is stationary. Admissible linear combination will be in effect if your W or Y is not stationary. But when W is stationary, then you are not asking yourself whether this linear combination is admissible or not. Therefore, here you are allowed to express this as a double summation lambda I, lambda J, R sub W, SI, SJ. Mr. Zawadi may want to raise this question. If you are allowed to write this and then compute this, and then if you want to simplify this, all you need to do is to multiply both sides of this equation by lambda I, and then take summation from I equal to 1 to n, and then replace this double summation with lambda I, summation of lambda I, R sub W, S is 0 is 1. Mr. Zawadi may want to raise this question. What is that question? If you are allowed to write variance of y hat to be variance of w hat, why you cannot do that out there? Here you can write variance of y hat equal to variance of w hat, and it's okay. But the point is this: you are not allowed to replace w hat with a linear combination. Are you clear? Here, it is okay to write this variance of w hat, but you cannot replace w hat with this linear combination. Because out here, you do have access to covariance of W, even when you are in scenario 6. But the point is that your estimator is not in terms of W, it is in terms of Y. In scenario 6, your estimator is in terms of Y, not in terms of W. Variance of R S0 could be written as variance of estimated value of y at the point which is not sampled minus true value of if you simplify this, you are going to get I from 1 to n lambda I W at Si minus W at S0. Here your W is stationary. When you are here, it is okay to replace this y hat with linear combination lambda I times y at Si. But it's not okay to say variance of this linear combination is equal to double summation, because covariance of y is not available. But covariance of W is available, because W is stationary. This will become a double summation, the first term, plus sigma 2 minus 2 times summation I from 1 to n lambda I WS0 SI. And then you can simplify this, writing it as I from 1 to n summation j from 1 to n lambda I lambda j r sub W Si Sj, this is the variance of the first term, plus sigma 2 variance of W, which is variance of y, minus 2 times summation I from 1 to n lambda I r sub W S0 Si. And then you can simplify this. You can either write down your variance of residual in terms of covariance of W or variogram of W. And I'm going to write it right away. What you need to do is to multiply both sides of this equation by lambda I, take summation from I equal to 1 to n, and then replace this double summation with what remaining. Summation of lambda I times this, and then when it comes to this part, please look at your note to see if this 0 is 1, is I or 0. Can you look at your notes? This 0 is 0 or I? This should be I. This should be I. And this should be I as well. Then summation of this, and then if you multiply by lambda I and then try to replace summation of lambda I from 1 to n, k from 1 to p with this part here, because you are going to have this part, and then it will become summation of k from 1 to p mu k f sub k s0. And then if it's going to be I here, then please pay attention. It's going to be I, coordinate of xi, and then it's going to be I, if you replace this with its counterpart, simplify it, you are going to get sigma 2 minus summation I from 1 to n lambda I r sub w S0 Si, and then plus k from 1 to p mu sub k f sub k S0. You can check to see if you could get ordinate region variance of residual if you put p equal to 1. If you put p equal to 1, you should get ordinate region variance of residual. See? The only change that you have to make if you want to have constant and unknown mean, you have to replace this W with nothing, just R. Because if your M is constant, then R sub W is the same as R sub Y, and R sub Y is the same as R. And then when it comes to this part, if P equal to 1, then F sub K is 1, and then you are going to have mu1. Mu1 plus this will be your equation for variance of residual. We denote this by sigma R according to our naming system, universal ordinary region as superscript, and you have to raise this to the power of 2. You can express your variance of residual in terms of variogram of W. How? What you need to do is to replace this with sigma 2 minus gamma. Sigma 2 will cancel out with that sigma 2 out of there, and it will become summation I from 1 to n lambda I gamma W S0 Si minus k from 1 to p mu sub k f sub k computed at S0. That's going to be variance of residual in terms of variable. Now, let me go through scenario 7. Mr. Ahmadi, what would be scenario 7? What you need to do in scenario 7, your mean is variable and it is given. When it comes to variance, your variance is variable. Step 1. Because M is given to us, therefore we can switch from Y to W via this relationship. And then, as we are given W at any station, then we can restate our problem in terms of W. Given for all I from 1 to n, then you are asked to estimate W at a point which is not sampled. That's a step 1. When it comes to step 2, you have to test your estimator. Your estimator can be written as a linear combination of W at S R. When it comes to step 3, you have to test your residual. Here, your residual is defined as estimated value minus true value. In step 4, you have to impose unbiasedness condition on your residual to see if you are going to get an additional relationship with unknown coefficient lambda. Expected value of residual has to be 0. And you have to put a question mark on top of this equal sign to argue that you are going to impose this relationship on your residual to explore whether you are going to get an additional relationship or not or not. Here, as you can see, because W is zero mean random function, if you replace R with what you have here, then take expectation from it, it's going to be automatically 0. It will not result in additional relationship. Therefore, it is okay. No additional relation. Step 5. When it comes to step 5, you have to compute variance of residual. Please pay attention. Please pay attention. When you are in scenario 7, neither Y nor W are stationary. Right? This variable variance simple as that your W is also not stationary. Because when it comes to expected value of W, expected value of W is still 0, which means that your mean is independent of spatial location. It's constant. But when it comes to variance of W is not constant, it is variable. Therefore, you have to be quite careful to avoid reaching either covariance of W or covariance of Y. Because neither covariance of W nor covariance of Y is accessible. See, Mr. Iliati, you are not allowed to say, okay, variance of the person is going to be a double summation in terms of R's of W. Why? Because R's of W is not available. Because W is not stationary. What should we do? We have to check whether we could write this term inside the bracket in terms of an admissible linear combination. If we can, then we can compute the variance of this linear admissible computation. If we cannot express this in terms of an admissible linear combination, then we can't compute variance of this. Please pay attention, this I is from 0 to n. You have to make a decision on whether this linear combination is admissible or not. For this linear combination to be admissible, summation of lambda I from 0 to n has to be equal to 0, which is not the case. As this linear combination is not admissible, therefore you cannot compute this variance of residual. And your computation will stop at the step 5. In a sense, you would say scenario 7 is dead end. You cannot go ahead and follow computation of lambda. Scenario 8. When it comes to scenario 8, your mean is variable and it is not given. And your variance is variable as well. In step 1, you have to check and see if you can switch from Y to W. As n is not given to you, therefore you cannot switch from Y to W. Not applicable. That's step 1. In step 2, you have to cast your estimator. Estimated value of Y at the point which is not sampled can be written as a linear combination of observations. When it comes to step 3, you have to cast your residual. Residual is defined as estimated value minus true value. In step 4, you have to impose unbiasedness condition on your residual. Please pay attention. Please pay attention. When you want to impose unbiasedness condition on your residual, you have to interpret this unknown here. What do we mean by this unknown here? By this unknown here, we mean these a sub k are not given to us, because we have already known f sub k. By unknown we mean this a sub k is not given to us. And we have to make use of this unknown value of a sub k to be able to impose unbiasedness condition on our residuals. Expected value of y hat at S0 minus y at S0. Expected value of summation I from 1 to n lambda I y at S I minus y at S0. You are not allowed to do something very different from what I'm going to say. What you need to do is to make use of linear property of expectation here and bring this expectation inside. It's going to be summation lambda I expected value of y at S I minus expected value of y at S0. And you could easily replace expected value of y at Si with m at Si minus m at S0. We can do nothing with this unless try to make use of this unknown property of mean by replacing this deterministic component with what we have out there. I from 1 to n, lambda I, and then we can replace this with summation k from 1 to p, a sub k, f sub k, computed at si. Minus k from 1 to p, a sub k, f sub k, s0. That is how to make use of a known property of a sub k. We can factor out summation k from 1 to p, a sub k, and then summation I from 1 to n, lambda I, f sub k equal to computed as I, minus now we have to have some descriptive discussion to impose unbiased condition on residual. We want to have these equal to 0. If we expand this, we should write a1 times this with k equal to 1, and then plus a2 times this with k equal to 2, and so on. For this linear combination to be equal to 0, we have no idea of a sub k, because a sub k is not given to us. All we need to do is to impose unbiased condition by saying this term has to be equal to 0. This is called unbiased condition or universality condition. I is defined internally, therefore you have to define k externally. Step 5. You have to compute variance of residual. Variance of residual can be written as variance of this minus and then this can be written as I from 1 to n, lambda I y at si minus y at s0. Please pay attention, you're not allowed to write variance of this first term to be a double summation in terms of covariance of y, because covariance of y is not available. If you replace it y at si with m at si plus w at si, and then replace it y at s0 with m at s0 plus w at s0, then soon or late you will end up with this term here, which is 0. This is 0, this is 0, this is 0, this is 0. Therefore, if you do this, sooner or later you will have I from 1 to n lambda I w at Si with I minus w at S0. Now, you have to check whether this linear combination could be put into a form for which you can compute its variance. How could it be possible to check? Because, by the way, again, Mr. Zohari, we are not allowed to say variance of this is equal to a double summation in terms of covariance of W, because covariance of W is not available. Fortunately, this relationship here implies that you can write this as an admissible linear combination. This linear combination is admissible. Why? Any comment? This linear combination is admissible. Summation of lambda I from 0 to n is equal to 0. Why? Because if you expand this, you are going to get, let me write it here. Summation I from 0 to n, lambda I is 0. Why? You can write this as lambda 0 plus I from 1 to n, lambda I. And you are told that lambda 0 is minus 1. And then this summation of lambda I from 1 to n is equivalent to put k equal to 1. If k equal to 1, then summation of lambda I is equal to 1. Therefore, minus 1 plus 1 is equal to 0. That is why we argue that this linear combination is admissible. If that is the case, we can write this as variance of, let's look at my editorial stuff. I can write this like this. And if you ask me why and how, what should I say? I can write this here, and as you can see, W is not stationary, but W minus W is the first increment. You can write this linear combination in terms of covariance of these two random variables. One is at S I and the other is at S J. Therefore, here you could write this as double summation I from 1 to n, j from 1 to n, lambda I, lambda j, covariance of W at Si minus W at S0. This is in first random variable to put under covariance argument. Then I have to separate this by saying W at Sj minus W at S0. I do know that the covariance of W is not available, is not accessible, but by writing this in this form, it is possible to write down the variance of this linear combination in terms of the variance of these two random variables. Now, once again, I would like to ask everybody to see how could it be possible to compute this covariance. You have to check scenario 4 to see what you need in scenario 4, and then you have to duplicate that when you are in scenario 8. Variance of y at Si minus variance of Sj. This variance is the same as variance of Si minus variance of Sj. Why? How can I write this variance in terms of W? Variance of this is equal to variance of this y. M is value. If you replace this with what? M at Si plus W at Si. And then replace this one with M at Sj minus plus W at Sj. This M of Si minus Mf at Sj is basically a single number. And that single number would not change the variance if you add or subtract it from a random variable. W at Si minus W at Sj is a random variable. And then M of Si minus M of Sj is a single number. If you add or subtract this number from this random variable, its variance would not change. That is why. Now, What I'm going to do is to write this as W at Si minus W at S0 minus W at Sj minus W at S0. If you look at what I did, this argument is the same as this argument, because this W at S0 will cancel out with this positive W at S0. Now, I can write this as variance of the first term plus variance of the second term minus 2 times covariance of the first term and the second. Variance of this can be written as 2 times gamma W S I Sj I can replace this with 2 times gamma W S0 Si plus gamma W S0 Sj minus 2 times covariance of I have to replace this covariance with what remaining. This covariance, if we divide both sides by 2, this covariance can be written as gamma W S0 Si plus gamma W S0 Sj minus gamma W Si Sj. Please pay attention. In step 5, you are asked to compute variance of residual. And if you want to compute variance of residual, you have to be able to compute this covariance. And this covariance can be replaced with these 3 terms here. Therefore, variance of residual can be written as double summation lambda I, lambda j, and then you have to replace this with what you have here. This first term can be put in separable term. You can write it as summation j from 1 to n lambda j times summation I from 1 to n lambda I gamma w S0 Si. When it comes to the second term, again it is separable. And then when it comes to the last term, it is simply a double summation. We cannot separate it. This part is 1. Why? Why is it 1? Because of unbiasedness condition. This part is 1 as well. Because of unbiasedness condition. And since I is dummy, this index of summation is dummy, which means that this is the same as this. You can write 2 times this instead of this to term here. Therefore, variance of residual is going to be let me write this as variance of residual to be 2 times summation I from 1 to n lambda I gamma w S0 Si minus double summation lambda I lambda j gamma w Sj. That is step 5. We manage to write down variance of residual in terms of gamma, not R, because R is not available for even stochastic compound. When it comes to step 6, in step 6 you have to test your objective function. That is your objective function. You have to minimize variance of residual. But this objective function is subjected to universality condition, which means that your f sub lambda, which is this one, this is subjected to universality condition. Summation I from 1 to n, lambda I, f sub k, si, f sub k, s0. This is universality condition. It's a typical optimization problem where your objective function is subjected to a typical equality constraint. At first, you have to incorporate this constraint into the objective function itself. How? T a new objective function plus 2 k from 1 to n mu sub k times this. This new objective function is no longer constrained. It is considered to be an unconstant optimization problem. And when it comes to step 7, you have to minimize this objective function. Partial derivative of g with respect to lambda I has to be equal to 0 for all I from 1 to n. Partial derivative of g with respect to mu k equal to 0 for all k you have n plus p equations with n plus p unknowns. Now, partial derivative of g with respect to lambda. You have to take partial derivative of this with respect to lambda plus partial derivative of this with respect to lambda. Look at what you have here. Partial derivative of this with respect to lambda will become minus 2 times summation j from 1 to n, lambda j times this. When it comes to this one, it will become plus 2 times gamma of w. When it comes to this one, partial derivative of this with respect to lambda I, it will become this summation, of course with 2 here, this summation mu k f sub k s I, because this time this has nothing to do with lambda I. Therefore, let me write it here in order to have everything clear for you. Minus, of course I divide both sides by 2. As you can see, J is defined internally, K is defined internally, therefore you have to define I externally. And analyze these conditions here. Again, I is defined internally, you have to define K externally. You have N plus P equation with N plus P unknowns. Please pay attention, when it comes to scenario 8, you cannot convert this to what? Covariance. Wow. You cannot convert this to covariance because W, gamma of W plus R sub W is not equal to sigma 2. That relationship is only applicable for a stationary random function. It is not applicable to non-stationary random function. Therefore, if you compare this to scenario 4, you can easily convert this to scenario 4 by just saying in scenario 4 n is constant as opposed to being variable. For n constant, p is equal to 1. And you can close your eye and eliminate this term. In that case, it will become this plus mu is equal to minus this, and this summation of lambda r equal to 1. That's going to be a step 7. In step 8, you have to compute lambda and mu by solving this simultaneous linear algebraic equation in terms of lambda and mu. When it comes to step 9, you have to compute your estimated value of y at a point which is non-sample to be equal to lambda I y at Si. That is how to compute variance of, estimated value of y at a point which is non-sample, which is our original problem. And then, when it comes to step 10, you have to do additional computation if required. Mrs. Doyle, would it be possible to tell me what is the difference between step 10 and step 10 of scenario 8 with step 10 of scenario 6? In both scenarios, you have 3 computations: variance of true value, variance of estimated value, and variance of residual. Can you tell me what is going to be the difference between step 10 of this scenario and step 10 of scenario 6? اینجا چی میشه؟
اینجا نیست، ثابت نیست دیگه.
We cannot compute variance of true value. Here we can only compute variance of residual, only. Not variance of true value, not variance of estimated value. Again, you have to replace this with estimated value of y minus true value of y, and then replace that with w all together, you are going to have this color variance of residue. And then if you multiply both sides of this equation by lambda I, take summation from y equal to 1 to n, and then replace this double summation out there with what remaining. You have to replace minus this, and then if you look at that part over there, it will become summation I from 1 to n, lambda I, f sub k, lambda I, gamma w, s0 si, minus summation. Now look at here. If you multiply both sides by lambda I, take summation from I equal to 1 to n, and then summation of lambda I f sub k can be written. Therefore, it will become k from 1 to p mu sub k and f sub k computed at s0. That's going to be your variance of residue. Now, up to now we have 8 scenarios. Could it be possible for someone in our class to tell me what is the unique feature of these 8 scenarios? As Mr. Zohri mentioned, the support size for observation is the same size as support size for estimation. What we are going to cover on Saturday, we are going to raise this question. Given a single partial realization of a random function, estimate the attribute under consideration over a block indexed at S0. Not at the point, but over a block. What does that mean? The support size for observation is pointwise, but the support size for estimation is block-wise. In these new 8 scenarios, we have 8 new scenarios, and for these 8 new scenarios, the support size for observation is pointwise, support size for estimation is block-wise. Altogether, it will become 16 scenarios. And it's a good example for upscaling. If you are given remote study sense data and you want to compare your ground-based measurement with air-based measurement, the very first thing that you need to do is to change the support size of your ground-based measurement to support size of your air-based measurement. And this question will address that assignment for you. How to move from point to block. از حوصله همیشه سپاس گذارم تا شنبه همگی رو خدا مسلم.